Good morning, ladies and gentlemen. This is a lecture to introduce you to a very important and topic, and one which everybody can get interested in. It's all about water. Water everywhere. But our take on this is, it is so little understood. And the message from this presentation is fundamental to everything you know about water. What you learn from this is, it is the structure of water, not its composition, which is important. There are three authors for this paper: myself, Professor Rustum Roy, Dr. Tanya Slavecki, and Dr. Manjulata Rao, these two brilliant young postdocs who work with me at Penn State's Materials Research Lab in the signature science of this major university. That's the speaker of today. Unfortunately, the two young colleagues of mine are not around to record their portions. I'll do what was said by the greatest person to write about how to understand healing was, it is more important to know the disease, the person that has the disease, than the disease the person has. So in his lecture you should also know, it is more important to know the speaker that gives the lecture than what he or she is saying. Okay, this is what I am. I hold 5 professorships at these various major universities. I'm elected to national academies, and I've spent 50 years championing the practice of interdisciplinarity in these fields of materials research, science, technology and society, science and art, science and religion, role of sex, money in culture. So that fills you in, and you could go to my website, of course. I want to stress that I'm a hard scientist. I don't only mean a rigorous scientist, I mean a person who works with hard materials. Our lab is well known for what we've done on diamond synthesis, or we work on rubies and all the silicon carbide, all the hardest materials on the earth. So we are not coming from any fluffy. So, but what is hard science? How does one describe it? I have a long list on my wall of my lab, in which we get quotations from Aristotle, Lao Tzu, to William James, to right down to Alfred North Whitehead, about 10 of these, emphasizing what I am saying here. So this is not some idiosyncratic definition of hard science. Hard science is one which deals with facts, solid, reproducible facts, reproducible experiments which connect cause and effect, which have been repeated several times, depending on how extraordinary the new facts are, and is repeated in other labs. What I have to say is, at the bottom of the page, explanations or theories are not, I repeat, not a part of hard science, not necessarily a part. They come later, and they change frequently. They do not alter the facts. Theories alter, they come and go on every subject in science. But what remains unchanging is hard science. That means well established. This is science. Now I'm presenting this as science for the citizen, not for the expert. The citizen who is really interested, useful science about water. This is not to get a PhD or to write another paper or get another citation. So let me start you with the first law of material science for the citizen. It comes right after the first 2 laws of thermodynamics. For everything you want to know about real ordinary science, the stuff you touch and feel and so on, like water that you drink, this is what you ought to know: the first 2 laws of thermodynamics, and then the first law of material science. And what is that? Since most scientists have never heard about it, maybe they'll learn something. It is that structure determines properties, most importantly, not the composition, but the structure of a condensed phase. A material is called a condensed phase. It's either a solid or a liquid. So it is structure that determines its properties, not the... Thousands of scientists, ignorant outside their own specialty. Unfortunately, that is the reductionist culture of science. They merely think of composition as the way to change properties. Add something to it. Aha! No. That's a routine thing to do. Obviously, it does change it. But the way to really drastically change properties is to change its structure. So because they believe in composition, so they always keep asking, is your substance, is your water or your solid pure? And if so, they say, oh, well, it's just water. And they assume, erroneously, as I will show you in a minute, liquid water always has the same properties. Nothing, ladies and gentlemen, could be further from the truth. Water comes in a myriad different structures with a myriad different set of properties. Now, this kind of silly argument has been used. We have no brief for homeopathy. We don't study much in homeopathy, or we don't do clinicals to show it's valuable. We are totally neutral about homeopathy. For 200 years, though, the science community, especially the medical guys, have used such a ludicrous argument against it that we have to correct that. They've never read the literature outside their field, and unfortunately, not having read the literature, they make pronunciamentos which are believed by the journalists who take their word for it, because they all went to high school and they learned that water was H2O. What we have done is laid that argument to rest, that if it is just pure water, it can't have different properties. So if you want to check on homeopathy, help yourself, but check its efficacy and compare it head to head with any other pharma products or whatever it is. Patient satisfaction, cost, all those factors if you want to check on homeopathy. Do not ever use again the now completely destroyed argument that if it has just pure water, it can't be anything different. We will show you how different it can be. This is science. Now I'm presenting this as science for the citizen, not for the expert. The citizen who is really interested, useful science about water. This is not to get a PhD or to write another paper or get another citation. So let me start you with the first law of material science. For the citizen, it comes right after the first two laws of thermodynamics. For everything you want to know about real ordinary science, the stuff you touch and feel and so on, like water that you drink, this is what you ought to know. The first two laws of thermodynamics, and then the first law of material science. And what is that? Since most scientists have never heard about it, maybe they'll learn something. It is that structure determines properties, most importantly, not the composition, but the structure of a condensed phase. A material is called a condensed phase. It's either a solid or a liquid. So it is structure that determines its properties, not the... Here are some building blocks. If you go to Martin Chaplin's website, just go to Martin Chaplin, it's enough. This brilliant man has collected over years and years with 6 or 7 million hits on his website all the structure of water information, of molecules of water, not of liquid condensed matter. Make the distinction. The chemists talk about structure and refer to these molecules, these little chunks, clusters. Those are the words used. They're small, like the one at the top left. You will see that's the sacred of all the things at which you must pray. It is to the molecule H2O, and you see that nice so-called hydrogen bond at 104 degrees angle and all that. Those are sacred statements made about the structure of water. They're all irrelevant, of course, but never mind. That little unit is combined in different arrangements, These are all hypothetical and calculated units. No one's ever seen one with a transmission microscope, anything like that, but they're reasonable arrangements which are probably present in liquids. But of course you don't know how many are present of A, B or C, but these are plausible arrangements of simple molecules of water to make these big blocks or clusters. But this is, studying this stuff, we wrote a seminal paper, and there's a reference in it, Material Research Innovations, Volume 9, page 577. It's a 40-page paper, so that's worth looking at if you're seriously interested. What is very important, it's a very crude cartoon. It's not got all the nice, sexy, three-dimensional, it's a virtual, nicely done presentation. I used it to compare why those molecules which Martin Chaplin shows so well can be connected. How would they be stuffed in? I've just stuffed them into a box and thrown them together. What is important is what is the bonding between the red part, which is kind of the H2O unit, and a cluster. And I've drawn black circles around a particular cluster. I mean, I don't know what they are, but let's take cluster A, B, C and D. Now what is very, very important is to note that within the black area, the bonds are largely those which you can see. They're short bonds, and they're kind of hydrogen bonds and covalent bonds and so on. And then if you look, you can't look at it of course, if you consider that the bonds between the black areas from one black area to the next one is very different. I'm telling you that. I can't show it there, but it's very different. Now that is the supreme argument that lies at the fundamental heart of what we are talking about. There are different, very, very different bonds. Some are strong and some are weak. There is a ratio probably of 1 to 500 between the weak bond between the black and black areas and some of the strongest bond between the oxygen to hydrogen bond. So huge differences in the bonding. That is what makes water so fascinating and so important, and why it is absolutely important that you grasp that water can be changed by such weak vectors. Pushing it here, acoustically, pushing it with a little light photon and so on. That is the inequality of bonding in water by a factor of, say, 500 to 1 at the edges, but of course many others in between. That is what is so fascinatingly explained now about the mutability of the structure. So this is a little introductory science for every citizen. You should really grasp it. Look at that nice sexy term, anisodesmicity. I think Linus Pauling, my mentor, the great crystal chemist of this country, talked about bonding as the key, and anisodesmic means unequal bonding, and this is highly unequal bonding, and it is the key to water's uniqueness. Now let me show you how dramatic this can get. And water is worse than what I'm going to show you, but I'll show you an example now. I call it the tale of two materials, diamond and graphite. These are both very common. Every citizen, adult here knows about diamond and graphite. Let's compare and contrast the properties and the structure. Now, if we, like the anti-homeopath crowd, were to say, well folks, it's just carbon. It's just carbon. They can't be different. Now you understand how ludicrous that claim has been by that group of people who rightly or wrongly have criticized homeopathy, but it certainly was for the wrong reason. It's just carbon, diamond and graphite. Wrong. It's just carbon. Diamond is the hardest material by far on the planet Earth, as far as we know so far. Graphite is one of the softest materials. It's in your lead pencil, so-called lead pencils. Every time you write with a pencil, you're breaking up graphite. Diamond, you break it up. Does your ring give way or something? Hardest material, softest material. Why? Now look at the bonds. In diamond on the left you see this arrangement of a 3D network in 3 dimensions. All the bonds are equal. Each one's bond length is 1.54. On the right hand side you see the layers of chains, a sheet of carbon atoms arranged in hexagons and tightly bonded to each other. Please look at the number. 1.43 angstrom for the length in the graphite. It is even shorter than the bond in the diamond. So you learned something today, that graphite in one direction is harder than diamond. What do you know? See? But now look at the other side. Between the sheets, there's a distance of 3.35 angstrom. Huge difference. So that the electrostatic forces, the bonds between the sheets of paper which make up graphite, are very, very weak. So when you move your pencil, those sheets break, and that's why you get a dark mark. If you were to do that with diamond, it would scratch any other material, make a hole in the other material. Exactly the opposite. So profound differences due to the anisodesmicity, unequalness of bonds. Now think of that when we'll be talking about water. Between those black units which I showed before, the bonds are like even weaker than the bonds you're seeing between graphite layers, and so they can easily be moved. The analogy is a beautiful illustration which something you, most of us in the audience, have experienced. We've seen diamonds and they don't wear out, and we've used lead pencils. So it's just carbon, doesn't go anywhere. It's just water. Is even more incorrect. So this shows a dramatic difference of anisodesmicity on equal bonds. Diamond was hardest material, very strong, equal bonds in all 3 dimensions. Graphite was softest material, even stronger within the sheets, but very weak in between. Unequal bonds means huge unity. So your key question. So how many kinds of liquid water are there? The answer is very, very many. Undoubtedly infinite. How long do these structures last? Some in our lab at least to hours and hours and days, and we have some for months, some for very long times near room temperature. Remember what I'm saying? Near room temperature, 25 Celsius to 15 Celsius, they last a long time. Why do we have so many? And how can you tell that they're different? So because they believe in composition, so they always keep asking, is your substance, is your water or your solid pure? And if so, they say, oh, well, it's just water. And they assume, erroneously, as I will show you in a minute, liquid water always has the same properties. Nothing, ladies and gentlemen, could be further from the truth. In thermodynamics, we've been terribly, terribly wrong. How can it be? For 100 years, I've been active on the bench as a professor for 60 years. So how have I made such a huge mistake for 60 years? Unfortunately, thermodynamics has a bigger black hole. We all dream about black holes in the universe and all that. That doesn't matter to anybody except the people who make a living writing about them. It's nice in astronomy and all that. I don't want to criticize that. But I'm saying it doesn't affect any citizen. Now this is much more significant. This black hole in thermodynamics has prevented us from utilizing the enormous potential of manipulating of water. Why? Because, I'll get a little scientific, in that we can find the changes of free energy, our understanding of science, and limited that agents for change were limited to 2, pressure and temperature. But there are several other ways we can change matter, we know that. Electric fields change matter. Magnetic fields change matter. Strain fields change matter. Epitaxy causes all kinds of interesting changes. What I'm using this fun term for, ignoring these is a real black hole of modern science. On the Earth, forget the skies, on the Earth, the biggest black hole in our science is that we ignored all the common vector and tensor fields which change matter. A huge hole, folks. It has opened up an entire field of research, but it's manifest first in the structure of water. Epitaxy is a particularly material science term, so I want to introduce you to it. It is the imprinting of one structure onto another without transferring any matter, especially from a solid to a liquid. We use it in the semiconductor industry routinely. Without transferring matter, we only transfer a pattern or information. Epitaxy is the transfer of information without any matter moving. Now, the power of these vectors has now been thoroughly proven in our and many other researchers' work on the most important solids. What do I mean by most important solids to you? I mean, you've got a computer, right? In the computer, what are the important modern solids? It's the silicon on which all your chips carry the information. It's the magnetic materials which hold all the information, that's your memory. And it's the insulator which prevents one from leaking into the other. We've taken the quintessential representative materials, and in 5 seconds, in a very weak magnetic or electric fields, we can destroy the structure totally. That's it, and you can go to our website up there and look it up. You can find that through my website and find all that data fully established, right? Nothing to say. So those vectors which I discussed, E field, electric field, magnetic field, and so on, are very powerful vectors, so we're not talking about anything simple. Nothing to do with water here. These are the most important solids to the modern American citizen. You better have a computer. Those are the solids which count, and we with a little electric field can destroy it. Now, in addition, we can even conceive of very weak. We can conceive. This is not a place that we are giving data. We can conceive an explanation for, remember I talked about hard facts. I've studied the literature thoroughly. I've studied the work of Professor Larry Dossey. If you want to look at work, please go to Larry Dossey's work. Look him up on Google and you'll see his recent and last 10 books in the last 10 years of the most thoroughly, meticulously documented effects which were absolutely baffling. Human intention. Can human intention actually change stuff? Well, it was balmy. Till I'm coming along and saying a little weak radio wave. You know, you're sitting in your room, you've got radio waves bathing you. They can change stuff. Well, maybe human intention can change stuff. Maybe that's called prayers. We don't know, but everything that we wrote off before is now fair game. There is no argument that physically you cannot change with very weak magnetic and electric fields. Now we know that there are some very decent magnetic fields around the body. There's intention fields of all kinds, and we'll see. I have now raised, therefore, the Gordian knot, because these can be seen as similar vectors. They're vectors. The intention has a direction and a mass, right? And it becomes an interesting new line for solid physical science research. Don't get the psychology people involved. This is just physical science research. What is much more important for us here is that such vectors have been shown to work in changing water, thoroughly proven worldwide for millennia, including the present. In other words, changing water has been something that has been discussed in such circles for a long time, and people have said it's impossible, etc., etc. Well, now we can also claim an explanation, even a plausibility for this in our scientific dialect. Now, my colleague Dr. Slavecki is not here, so I will talk about what she did originally in the presentation in California. Here's what we do. We can change water by suspending charged nanoparticles. That's a colloid. A more proper term is aqua sol. Now, among the colloids, you can have silver colloids, which I will talk about in a minute, ultra dilute, stuff like that, homeopathic stuff, holy waters, coming from the waters of Lourdes or Venezuela or wherever, which are special. And now we say, oh, that may have a special material in suspension. We know that certain minerals are suspended and they have strong electrostatic fields around them, etc. Plausibility now. Sudden, when you give structure changeable by fields like electric, magnetic fields, and then you let loose the epitaxial potential of such suspended materials, you've got a whole new ball game. I can also change it by radiation, and I'll show you in a minute. Microwave, radio frequency, and of course light, which is a million times stronger, and so on. And this is all made possible by two terms which I will not have time to discuss, but please keep following the literature. Resonance, you all know about Ella Fitzgerald and breaking the wine glass, and I know everyone kind of poo-poos and says, oh, we don't understand that. Well, folks, we can now tell you all about that. It is simply resonance, and Mr. Planck and Mr. Einstein both explicitly in their classic papers of 1899 and 1905 excluded exactly what we are talking about, resonance. And even they didn't go further about the nature of the polarization of these radiations, because that's another little wrinkle you can put in. How do we look and study these things? We don't do a lot of elaborate stuff. We do simple stuff which anybody can do in a lab with a $10,000 piece of gear. pH, surface tension, zeta potential, and spectroscopy, Raman of course, and Fourier transform infrared and UV vis. And of course we do chemical analysis when we need it. The Raman spectrum that we use is particularly interesting because we take one where you can dip the probe right into a beaker. That's nice. And don't worry about all the details here, what are the modes and all that. I want you to look in the top right at a typical Raman spectrum, which we have run, say, a few thousand times. And you see that big peak, which means it's really absorbing light at that point. And the wavelength of the light you see, well, in that case it's Raman shift, is about 3500 nanometers. You notice those shapes, and those are when they stretch up and down. And then if you bend the bonds, you see them around 2100, and the ones that bend even weaker, you see that at 1500 nanometers. So keep that image fixed. That's the Raman spectrum, the signature, as it were, of the structure of water. Now I'll just give you the kind of stuff we do. We got from a doctor called Sue Benford 3 specimens in water of homeopathic remedies. Our job has nothing to do with saying where this DAX homeopathy works. We know nothing about that. We're just showing you that the potencies and all that stuff, when they shake it up, if you shake it up more, it changes. That's all we can tell you. It's different. Look at the green and look at the red and the black. It's different. And we can do it blind and all that stuff. It's different. And you can get to all the details. I'm not even interested. I'm just telling you one fact. Different homeopathic samples with no different in composition are different in structure. So my colleague, brilliant young woman, Dr. Ra, and she has run, as I said, several hundred, over 1,000 Raman spectra, I'm sure. So what happens when we add a few parts per million of silver to water? We're talking, say, 10 ppm, right? And that's, by the way, that's 1 atom ppm. When you take, if you subtract for the, in numbers of units, it's 1 atom of silver per million atoms, molecules of water. So please notice the difference. So there are structural differences caused by the addition of those teenies to that. She's an experienced scientist. So what is a colloid? We permanently suspend them. It's important. Fine particles, solid particles, dispersed permanently in water or any liquid is called a colloid, right? Milk is a colloid, blood is a colloid, mayonnaise is a colloid, so you know that very well. Now we can structure the water with nanoparticles. Einstein's, whose most cited paper, by the way, is his Brownian motion paper about colloids. Okay, a colloid acts like an atom. He implied this in 1905, and this was a very important topic. These funny mixtures of solids suspended in liquids permanently. 3 Nobel Prizes were given before, about the time Einstein got his Nobel Prize. 3 Nobel Prizes were given for colloids. 2 in 1 year. 2 in 1 year. So this is a very important topic, not some science. Now I want to tell you kind of wonderful usability. Here's colloidal silver. They make a dispersion, and it is so good because this stuff enhances the life usability of any antibiotics, because bugs don't learn to use silver colloids and then get immune to them. Wonderful. So you can, by mixing it with regular antibiotics, you can extend their useful life. Isn't that a wonderful thing? First, they kill bugs as well as any other antibiotic. Second, they extend their life. Isn't that great? 99.99999 parts of water is doing as well as penicillin. Interesting. Then they even go further than some of the antibiotics. These are preliminary data from a big hospital in India. And you know, HIV, what do you know? If you can do pretty well with nanosilver. And in fact, they do very well on malaria. Here's the biggest lab, UN certified lab, everything else. And the director is saying it kills falciparum, which is the worst kind of malaria. So this is not something weird, far off. This is one of the really most significant opportunities. I'm amazed, I can only say stunned, that the Gates Foundation has not said, hey, look at this all over the world. Give it to 10 labs all over. If this is true, and you can grind out pure water to send all over the world, and the people who take it just drink it 3 times a day, that's it. You don't need any attention, you don't need anything else. It goes even further. It attacks some most amazing things. Here's a patient with leprosy. Now, leprosy is not exactly a favorite common topic, but there it is. It's with a little gel of that. So summary on colloids is, it's well established that colloidal silver is an antibacterial agent. It extends that, works on viruses. What can we expect from the proper scientific utilization of different colloids, of different metals, different materials, not only metals, and that there's going to be a whole pharmacopoeia of colloids. Now we come to radiation. One way to change water, I said, was put in colloids. Another way to change it is radiation. Let's start with a big, strong waves. You know, these are 10,000 times weaker than light above your head, right? These are microwaves, like your microwave oven. Except he does one thing, he polarizes the beam. He sticks it upside down in the water, and therefore you get a magnetic field in one direction, electric field in the other direction. By golly, he produces a different kind of water. And he noticed that it corrodes plastic. It even attacks stainless steel. So how can all that be? Just water boiled by being exposed to a polarized microwave beam does those things. So he sends it to us, and here's what we find. Holy smokes. Look at the change. Go from the black to the blue, and then you get way down to the red. That's what we got. This man sends us the water from Phoenix. We run it, and we say, wait a minute, what's that doing? If it heats up or warms up, it goes to green, goes back to blue, and back to black. Fade to black. What does that prove for us? There's no chemistry. The same water sample with time in the same beaker, never been touched. Pure water, radiate it, it changes. Let it relax, it goes back. QED. Pure water can change its structure simply by being radiated with a microwave. Let's go further. Here's another man called Mr. Kanzius, wonderful friend, inventor of the RF generator, which he uses. It's at a short wavelength, a short wave radio, regular microwave beam, except he tickles it. He polarizes it in a special way, just like Polaroid lenses are used and you cut out a light and you're dark. He polarizes it in a special way. So a polarized radio frequency, common frequency beam. That's all it is, ladies and gentlemen. It's not all, it's a pretty tricky polarization, but your frequency. And here's the team. When he did it, announced it on YouTube, etc., the whole world went crazy. Scientists called him an absolute idiot, a madman, blah, 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 and all. I'm talking about 10,000 emails, so you can really see that. So we brought it to Penn State, to my lab. This is our group. You can see all my colleagues there. And we said, let's do it again. And we did it. Remember the hard facts? That is hard science. We repeated it. It's done. And here's what we got. This is his machine. It is on the right hand side, that grey box, and out of it is poking a little beam. And when you bring a test tube full of water, this happens to be slightly salty water. We can see bare, not salty. It's down to 0.1%. We can do it. This was done at higher concentrations. And you see the way it goes. It burns. As soon as it hits, it burns. Now, on the right hand, last one you see is you can do it, and if you don't ignite it, they don't ignite. Pure water. Look at the last one. It's DI water, absolutely pure, doesn't ignite. Then we take that water and we do the same thing, and look at that red line. Black line is the standard water, remember. Look at the red line. That is how much we change it. That's the main absorption frequency of water. We have dropped it by a factor of 3 or something. That's pretty weird, right? So then we let it relax and it goes back up and so on. You can see also the emission spectrum from that. It's got the sodium line and nothing else. So we've done the usual stuff. Now, in case you're worrying about something else, the blue little line up there is the end of a pipette. From it is dropping a drop of seawater taken from the Sanibel Island just outside the house of Mr. Kanzius and dropped into the beam by Mrs. Kanzius in their home. And look how it catches fire. The whole light. No lighting matches, no nothing. And that's one drop of water is giving you that flame. So it's like as though you were igniting alcohol or gasoline or something. Please note, drop of water burning like that. You say water can't burn? Well, folks, too bad. Summary. The facts are voluminous, indisputable, and compelling. What are they? That even very weak radiation can and does drastically change solids, which I've told you about, and liquids, as in water. And we have shown some very spectacular effects. So they're not going to disappear. These are not in the noise. So we're accepting them. What is the future? The new vectors for designing water-based products for use in major industries and for maintaining health, for causing healing, it's just legion now. The opportunity is just, the sky is the limit. We already know for sure that we can change it and retain it for simple experiments. If you want to look at some of the data, please go to rustumroy.com and you will see all the details. Structuring of water by colloidal silver or by radiation now becomes possible for the human race, and we think it is the most benign, easiest vector to use for many, many processes. And the things that we have used are electromagnetic. I also tell you that sound can do just as well, acoustic, vibrational and subtle energies, and maybe human intention. And we are all doing this because of the use of resonance, that peculiar phenomenon which Planck and Einstein explicitly ignored, and polarization. So a whole new field awaits us, and people should who wish to know more or come to us to do this kind of work, we are very happy to talk to them.